So let's talk briefly about unit vectors. So unit vectors basically are just vectors that have a magnitude of 1. So unit vectors are vectors that have a magnitude of 1. Okay, so the size of them are equal to 1. And they're really helpful because they help simplify a lot of different types of operations. So how do we convert a unit vector? So basically it's very self-explanatory. So a unit vector is formed by taking the vector of choice and then dividing it by the magnitude of that vector. Okay, so this it's not that difficult to do. So let me go ahead and give you an example. So let's say we wanted to find a unit vector in the direction of v is equal to 4, 9. So let's say we wanted to figure that out. So don't get confused so much by what it says by in the direction. The direction is already given to you. 4, 9 is going to go this way. So the direction is going to be there. But we don't want this size of the vector. What we want to do now is we want to compress it so that instead of having this size, it's going to have a much smaller size, size 1. Okay, so we still want it to be pointing in that direction, but we want it to be size 1. So in order to find this unit vector, all we have to do is take the vector that we have, which is 4, 9, and we're going to divide it by the magnitude. And the magnitude we already know how to do. We're going to take 4 squared and then plus 9 squared. Okay, so now we're going to take 4 squared, which gives me 16. I'm going to add it to 81. That's going to give me the square root of 97. Okay. So now what we want to do is we're going to just divide each of the components by the square root. It's going to be the square root of 4 over 4 divided by the square root of 97. And then 9 divided by the square root of 97. And one of the things that you can do with these vectors is that you can kind of see that if I take the magnitude of this, you'll see that this is going to be size 1, and I'll let you guys do that on your own. Okay, so now what we're going to do is we're going to do a couple of vector operations. Okay, so here we're going to talk about vector operations. So how do we add, subtract, and multiply vectors? Okay, so the first thing to kind of know is that it's kind of the obvious. If you have a vector that has components a1 and b1, and you have another vector v that has components a2, b2, then basically when I take the sum of the two vectors, it makes sense for me to just add the individual components. So just a1 plus a2, comma b1 plus b2. So that's basically the first one. So if I wanted to add two different vectors together, we're just adding the components. Same thing with vector subtraction. So it'll just be a1 minus a2, b1 minus b2. Okay. And then you also have scalar multiplication. So let's say you wanted to take k and multiply it by a vector u. Then in that case, all you're going to do is take k, multiply each of the individual ones, a1, k times b1. Okay, so here k is a scalar. So just a number. So, which just kind of makes sense because that's kind of what we did over here, right? This number was a scalar and I just multiplied each individual component by that scalar. Okay. Later on, we're going to talk about something called the dot product, but we won't get there just yet. Okay, so let's do a couple of examples of vector addition. So let me just do one example of vector addition first, because I want to show you guys something also. So given that u, so the vector u is 4, 5, and v is, I don't know, 3, 8. Okay, so what I want to do is find u plus v and graph u, the vector v, and the vector u plus v. Okay, so that you can see kind of graphically what that looks like. So we're going to start off by adding them. So adding them shouldn't be that difficult. All we're just going to do is add up the components, 4 and 3. That's going to give me 7. And then 8 plus 5 gives me 13. Okay, so that's going to be the sum of these two vectors. Okay, now what I want to do is graph them. So let's go ahead and graph these guys. So here's x and y. So we're going to first start off by graphing u. So u is going to be 4, 5. So it's 1, 2, 3, 4. Then comma 5. 1, 2, 3, 4, 5. Okay, so this one's going to be right there. Then you're going to have v. So v is going to be 3, 8. So this 3, 5, 6, 7, 8. So this guy's going to be over here. So let me just draw the vectors. Okay, so I forgot the green one. So there's this guy. All right, and then the other one is this guy. Okay, so this is vector u, and this is vector v. Now we're going to add u plus v. So u plus v is going to be the 7, 13. So 1, 2, 3, 4, 5, 6, 7, 13, 8, 9, 10, 11, 12, 13. So here's 13. Okay, so this is going to be 7, 13. And what you should notice is that this vector, the sum of the vectors, actually is right in the middle between the two vectors. Okay, and basically the reason why this is something called the parallelogram law. So what I can do is that, remember that vectors, we can just move them. So I can move this vector u up here. So this guy right here is also vector u. Okay, so this is vector u. And then you can also move this vector right here, this one up here. So this guy is also vector v. And you can see that this looks just like a parallelogram. So the resultant, which is basically this guy, we also call it the resultant vector, is basically the sum of two different vectors. So if I were to take two vectors and attach them by the tail, then the sum of the two vectors is going to be right at the diagonal, as if I had two of the other vectors just, if I just pick them up, whoops, I erased everything. If I were to just pick them up like this, and then the resulting vector, which is going to be the sum of the two vectors, will be just right there. Okay, which is pretty cool. Vector subtraction works the same way. The way that you would subtract two vectors is that, imagine that this is u and this is v. Well, one way that you can just do is just take the vector and then just move it the opposite direction. So this is going to be negative v. And you'll see that this guy going that way is actually going to be, well, actually, no, that's wrong. This is going to be u. And you'll see that actually the difference is going to be along those sides. So you can do this many different ways. But yeah. So one of the things that, if you didn't quite understand it geometrically, but you understood this is fine. I just wanted to show you what exactly you're doing, how the vectors look in a geometric fashion. So let's do a couple more complicated problems, or some that are a little bit more abstract, or with more math. So let's say you are given the following vectors. So you're given vector u, that's negative 3, 5. And vector v, that's going to be, let's say that's 6, minus 4. So you want to find the following. So first, let's find 3u plus 2v. Okay, so basically what you're doing is that you're taking this 3 and you're multiplying it by this vector. So you can kind of think about 3 times u as making this vector 3 times as large. So basically, if this vector was this guy, when I multiply it by a factor of 3, you're just making it 3 times as long. Okay? Whereas this guy right here, you're taking the vector v and you're making it 2 times as long. And then once you do that, you're just going to add the two vectors together and see what you get. So remember scalar multiplication, I can just basically distribute this guy, multiply each individual component by the scalar multiple. So this is going to be -9, and this is going to be 15. Then this is going to be 12, and this is going to be -8. Oops. Okay. And now all we got to do is just add the individual components. So you're going to have -9 added to 12. That's going to give me a 3. And then you're going to have 15 minus 8. That's going to give me a 7. So this is going to be the result of that. Okay. Let's say we have part B now. And in part B, what we want to do is take u minus 1/2 v. Okay. So basically here, what you're doing with the vector v is that this is vector v, okay? Well, it wouldn't look like that. It actually would look 6. It would go downward. So if you want to have this vector, then what's going to happen is that you're going to take this guy and make it half of its size, okay? So this is going to be u -3, 5, and add it to 1/2. Oh no, subtract it. 1/2, 6, -4. So you're going to have -3 and 5. Leave the negative outside. I'm just going to put in the 1/2 in there. So this is going to give me a 3, and this is going to give me a -2. And then what you're going to do is subtract these. So this is going to be -3 minus 3. That's going to give me -9. Okay. No, that's wrong. Oh my God. -6. Then 5 minus -2 is going to give me +7. Okay, so this is going to be my solution. Okay. Yes, so one other thing that I kind of want to look at is that remember that when I had 3, 2, you had in IJ form, it was this. So now that we kind of have those properties, let's show that this is actually going to be the component form. So remember that I is just equal to 1, 0, and then J is just equal to 0, 1. So when I can distribute this guy, and you get 3, 0, and then distribute this guy, and you're going to have 0, 2. And you can see that when you add them, you're going to get 3 and then 2. So you still get the component back. So I and j are vectors. So if you kind of look at them, at the vectors themselves, you can see that I goes in this direction, j goes in this direction. So these are standard vectors, okay? So here is 1, 0, and here is 0, 1. So just a really nice way to just rewrite vectors. Okay, they're unit vectors, and that's kind of how they work. If ever you have a component of 0, like 0, 3, how you write it in IJ form, you would write 0i plus 3j. But you don't really write the 0, so you could just say 3j. That's just what you would say. And if there's no I, that would mean that it's just equal to 0. Okay, so to end this particular section, we're going to talk about horizontal and vertical components. Okay. So sometimes you're not going to be able to get the components themselves. So if you are given the magnitude and the direction, then you can figure out what the components are going to be. So v is a vector with magnitude of v and direction theta. Okay, so one way to kind of denote it, so like if v is equal to a1 and then b1, okay, then a1 is equal to the absolute value of b cosine of theta, and b1 is equal to the absolute value of v, the sine of theta. So if you wanted to figure out the components, this is what it's going to be. So you can kind of think about it as the components of the vector v is going to be equal to taking the absolute value or the magnitude and then cosine and then the sine. And if you write it in ij form, it'll be v cosine theta I plus v sine theta j. So if you wanted to write it in the two different forms, that's basically how you would find the component form. So if you're given the direction, and here, when we're talking about the direction, theta starts at the positive x-axis. So that means when we talk about the direction itself, then we're starting here and then we're going all of this angle theta. So if my vector was going this way, this entire thing would be theta. That's basically what I'm talking about. Now, why are these formulas it? Well, if you kind of think about it, you kind of can think about it in terms of polar form. Because if you think about it in terms of polar, if you wanted to figure out if this is A1 and this is B1, okay, you know that this guy's going to just be the absolute value. If this is the angle theta, you can see that the cosine of theta is going to be equal to A1 over V. I move that over, you can see that A1 is equal to the magnitude of V cosine of theta. So that settles that. And then you also have the sine of theta is equal to B1 over the magnitude of V. So B1 is just the magnitude of V sine of theta. So that's basically where this comes from. So you can kind of see that all the complex number stuff that we did and all the polar stuff that we did, kind of it's all intertwined. So they're basically all kind of the same formula. So these are just the components, okay? So let's just do a really quick example on doing finding the components, and then we'll do an application problem in the next video. Find the vector of length 13 and angle of 225 degrees to the positive x-axis in I and j. Okay, so here what we want to do is let's create a vector that has a length of 13 and an angle of 225. So this is basically the direction. So they give you the length and the direction, and obviously 225 is from the positive x-axis, and you want it in ij form. Okay, so if I wanted to figure out my vector with a1 and then b1, or you can call it a and b, doesn't matter. Notice that a in this case, or a1, is just going to be equal to the magnitude of the vector times the cosine of theta. The magnitude is just going to be the length, which is just 13. And then we're going to take the cosine, which is 225 degrees. Okay, so when we do that, you're going to take the 13 cosine of 225 degrees. That's going to give me about, oh, my calculator's not in the right measurement. So 13 cosine of 225. I'm going to end up getting about negative 9.2. Negative 9.2. And then I'm going to take B2, and then the sine theta. So this is going to be 13 sine of 225 degrees. Okay, so if I do that into my calculator, you're going to see, well, they're going to get multiple things. So the first one is, let me put it into, so it's going to be basically the same thing. So notice that in your calculator, if you have the TI-36, you can get the both exact form and the decimal form. So the exact form will be negative 13 square root of 2 over 2. Negative 13 square root of 2 over 2. So that's what it would be, the exact vector. If you want the approximation, it'll be negative 9.2, negative 9.2. This will be the approximation. Now, the only thing to kind of just know is that we do not want it in component form. We want it in ij form. So that will be kind of easy, because that's going to be just negative 13 square root of 2 over 2 I minus 13 square root of 2 over 2j. And obviously you can write negative 9.2i plus a minus negative 9.2j. So that's kind of how you find the component form. In the next video, we will do 2 word problems, and we'll talk a little bit about direction as well.